project interim report for a CSC 577 recommendation systems. Um, I think the more interesting thing about our project is we are looking at unary implicit ratings to recommend news articles. So, um, what that actually means is that we're using clicks as our feedback. Click being a 1 as a rating and no click being 0 as a rating, right? So this is obviously very different from what we've learned previously in class, or around the algorithms we've learned previously in class, which has mostly been around explicit ratings, 5-star scale ratings. So naturally, that led us to having to implement our own algorithm. So this is an algorithm-based project where we'll use Keras to implement a deep learning model to build our recommendation system. A little bit more about this. We use a multi-layer feed-forward network that's based off user history. It's essentially a content-based recommendation engine. We'll talk about it more a little bit later, but we use doc2vec embeddings on user history. We have not completed this piece yet, but we'll also be implementing a restricted bolts machine, which won the Netflix Prize in 2007. And finally, we created 2 baseline models to compare models against the item KNN and the content-based TF-IDF with cosine similarity. Now, because the surprise package is only for explicit ratings, we use Ken's lens kit for the item KNN. So here, lens kit, you see we have out-of-the-box support for implicit feedback, and so easy you can just set a flag as feedback equals implicit, right? So for our data set, we used 2 pieces from the Mind data set. So the link is here. But basically the Mind data set is Microsoft News data set, English data set for news recommendation research. Very easy to download. We use the Mind Small data set, which is random sampling of 50,000 users, just so we can, get the project off the ground. Still leads to millions of rows in our training data. And so in terms of our actual data and what it looks like, we have, for every impression on a news article, let's say that at the point of you visiting a certain website owned by Microsoft, like let's say MSNBC or something like that, the news ID represents the article that is shown on a certain page on there, and your impression, whether or not you saw it, is represented by you seeing this, and the rating is click, 1 for click and 0 for not clicking, right? Your history is all the articles you've seen before. So these are all the news IDs for your user history, delimited by a space. And so we also have the news data set. Aside from the user behavior data set, this is the news data set, which shows us category for news and our text. Our text is made from concatenation of the article title and the article abstract. So you'll see that we also have a very imbalanced data set. Just like in real life, most of the time you see a bunch of news articles on a website, you don't click most of them, right? So we deal with that imbalance later on. And here's just the news categorical distribution. Most of it is about sports and news, with finance coming in third. So just an overview on the actual algorithm. So like I said, we use Keras to implement a deep learning model with doc2vec embeddings to build a recommendation system. So it's a multi-layer feed-forward network. And we use the user history, which we talked about up here, right, before the impression, to train our model, right? So what doc2vec does is it's an aggregation of word2vec. Word2vec is essentially you give word2vec a word, out comes a vector, and let's say you take a 128 size vector for each word, right? Well, now you have the size of the document times 128. That's the size of it's essentially a matrix, and so doc2vec aggregates that. I think by taking the mean to create the document level embedding. And so here's a little bit more of our implementation, which you can read more about. But like I said, essentially we take 128 dimension doc-to-vec embeddings using the user history. You create feed-forward networks, and we do some undersampling to take care of the imbalance in the data. So it'd probably be helpful if I just show a little bit of the notebook. So here we do our embeddings, and then we do some undersampling to get a perfect balance between our click and no click ratings classes. Here's our feed-forward network. It's very, very simple. You know, we have about 3 dense layers. It starts out wide and gets smaller and smaller. Actually 4 dense layers, sorry. And then we have an activation layer at the end, which is sigmoid, because this is, you know, click, no click, essentially, similar to classification. We have some dropout layers in between. And then we use an atom optimizer, binary cross-entropy loss. And yeah, I won't go into the baseline models because we've essentially, you know, covered those in class very closely. For evaluation, we've decided to go after precision at 5, recall at 5, precision at 10, recall at 10, NDGC at 5, NDGC at 10. We actually are not particularly interested in these NDGC metric, but in the Mind challenge, it was, you know, one of the metrics they used. So we figured, why not just see how we compare against these people. So yeah, these are our results. The item KNN, oh sorry, does not do too bad in comparison to the Mind challenge participants. The final person, 304th place person, has a NDGC at 5 at 21, and then we have one of 13. You know, not great, but at least we show that we're doing something. Our TF-IDF plus cosine similarity is actually terrible. It is close to 0. So I think the word embeddings, or the doc-to-vec embeddings, is what really made the feed-forward network very strong. So you see our precision at 5 and recall at 5 is very strong, especially as well as the precision recall at 10. We still have not computed our NDGC at 5 and 10 for the feed-forward network. So that's something we need to do. So that's outstanding, an outstanding task for us. The other thing that's outstanding is we've only begun to implement our restricted bolts machine. And we, you know, given that our feed-forward network has done so well, my intuition says that the restricted bolts machine will do well as well, if not better than the feed-forward network, since it is a well-known algorithm for recommendations in the deep learning recommender space, especially if we use the doc-to-vec embeddings for pre-processing. And that is our project. Thank you.